This is a video for AQA Further Pure Mathematics, Matrices section 3.6, Inverses and Transformations. We know that multiplying by a 2 by 2 matrix is a linear transformation. So multiplying by the inverse of the matrix can be thought of as reversing that transformation, i.e. it's the inverse transformation. So as an example of that, if we've got P mapped onto Q, which is 4, negative 2, under transformation A, then what we're saying is that the matrix A, 2, negative 1, 4, 3, multiplied by the vector for P, let's call it xy, must be equal to 4, negative 2. And therefore, we need to multiply both sides by the inverse of this matrix, so that xy, we're multiplying on the left, must be, when we swap the leading diagonal, 3, 2, change the sign on the other diagonal, and divide by the determinant. The determinant of the matrix is 6 minus negative 4 is 10, so it's 1/10 of that multiplied by 4, negative 2. So this here being the inverse of the matrix. And if we calculate that, we find that we get 3 multiplied by 4, 12, plus negative 2 is 10, so that's equal to 1, 1/10 of that, and then negative 16, and then minus 4 is negative 20, and 1/10 of that is therefore equal to negative 2. So P has got coordinates equal to 1, negative 2. So let's consider some of our standard results and their inverses. And reflection, first of all, in the x-axis. Well, if you think about taking some object and reflecting it in the x-axis, then to get back to where we started, we need to reflect back again. So we should expect that if this is our reflection R, then the reflection R inverse would be exactly the same. So we'd expect that these are inverses of each other. And of course we could check that by multiplying by itself. And if we do that, we get indeed the identity matrix, which is 1, 0, 0, 1. So yes, this is self-inverse. Reflection is its own inverse. Likewise, if we could reflection in the line y equals x, then again we would expect that to be its own inverse. And if you look at the matrices 0, 1 and 1, 0 and multiplied by 0, 1, 1, 0, again that is equal to 1, 0, 0, 1, the identity matrix. So yes, reflection in the line y equals x is self-inverse. Well, what about rotations? Well, the rotation, which is a 90-degree rotation about the origin in the anti-clockwise direction, is certainly not self-inverse, but we can think about what we would have to do. So let's think about the rotation. We've gone from our unit vectors I and j, and firstly rotated in direction anti-clockwise, so we end up in this position. So to get back to where we started, we need to rotate back again. So we need to do a rotation which is clockwise, and that's given by a matrix which is 0, 1, negative 1, 0. Always worth checking the determinant for a rotation. So here we've got a determinant of 0 minus negative 1, which is 1. So that's what we'd expect for a rotation. And of course we can check that that rotation, which is 90 degrees clockwise, does indeed give us the inverse by simply looking at the multiplying the two together. So we'd have to take these two matrices, which represent the two transformations, multiply them together, and of course we get the identity matrix. A rotation by 180 degrees about the origin, well, that of course we can consider as being self-inverse, because if we rotate 180 degrees twice, then we end up 360 degrees, which is back where we started. So yes, we should expect this to be self-inverse, and again checking that it is by multiplying by itself, and you end up with the identity matrix. So yes, rotation 180 degrees, self-inverse. If we now think about an enlargement, well, what happens in the enlargement is we get something which is linearly k times bigger. So to get back to where we started, we need to divide by k, or do an enlargement of 1 over k. So we would expect that the inverse matrix is going to be 1 over k, 0, 0, 1 over k. In other words, it's an enlargement by a scale factor of 1 over k. And if you multiply those together, then yes, we get the identity. What if we were to look at a matrix product? Well, we've seen in previous video that if we have a product AB and we want to look at the inverse of that, then that is B inverse followed by, I beg your pardon, it's B inverse A inverse. Now AB is transformation B followed by transformation A, whereas B inverse A inverse is the inverse of A followed by the inverse of B. So you have to do things in the opposite order. If we do transformation B followed by A, and remember that's the way we would write it, writing from right to left, then you must do the inverse of A followed by the inverse of B. I often think about this as putting your shoes and socks on. When you're putting them on, you put your socks on followed by your shoes. When you're taking them off, you take your shoes off and then your socks. So you do things in the opposite order to undo them. So a rotation followed by a reflection. To undo this, you'd have to do the undo the reflection and then undo the rotation. In 3 dimensions, things are not really any different in that the inverses of reflections are going to be reflections, the inverses of rotations, rotations, and the inverse transformations undo whatever the transformation has done. Well, here's a rotation matrix in 3 dimensions. You could check with the calculator that the determinant of this is equal to +1, which is what we'd expect for a rotation. And then you could also check that the inverse of that, M inverse on a calculator, gives you a rotation as well. This happens to be a rotation about the z-axis by 90 degrees in a anti-clockwise direction, so that the inverse matrix will be a rotation 90 degrees about z in a clockwise direction. Well, that concludes this video on transformations and inverses. In the final video of the series, we were looking at solving 3 simultaneous equations.